Our topic today says or is volumetric analysis. As I said earlier, this is the aspect of practical chemistry that deals with titrating a particular solution, usually an acid, with another solution, a base. The acid is usually tagged A. As you can see, this oxalic acid tagged A, and also the base tagged B, which is potassium KMNO4. The IUPAC name is potassium tetraoxomanganate 7. Potassium tetraoxomanganate 7. Now, in volumetric analysis, lab apparatus are usually used, such as the measuring cylinder. This is 1,000 ml measuring cylinder. We use this for measuring water, volume of water, when preparing solutions. When I say preparing solutions, it entails dissolving salts. When I say salt, this is an example of a salt. Substances in this form, we call them salts in chemistry. For example, most of the reagents you're looking at came in form of salt, but they can as well be prepared by dissolving a particular sample, a particular mass, in 1,000 dm cube of water using the standard measuring cylinder. Now, this is another measuring cylinder for measuring reagents of smaller volume. This is just 100 ml. This is an example of a reagent bottle with oxalic acid stored within. This is the conical flask, a measuring cylinder, reagent bottle. Here we have the litmus paper, which is an indicator. We have both red and blue litmus paper when it comes to volumetric analysis. We use the litmus paper, which is an indicator, to know which of the reagents in the laboratory is either a base or an acid. For example, when you step into the lab and there are maybe a set of reagents without name, how do I know that this is an acid? How do I know that this is a base? For example, one of the best ways to know which is an acid, if I'm to pick up a reagent here, is through the use of litmus paper. This is oxalic acid. How do I know, assuming there is no name here, how do I know that this is an acid? It is through the use of the blue litmus paper, because acids generally turns blue litmus paper red. For example, you can see this is a blue litmus paper. All I need to do is to just moisten it. It is still blue litmus paper. Then you carry out this test, take it very close to the acid. It becomes red, which is an indication that the liquid here is, or the reagent here is an acid. So you can as well do the same for a base. Assuming the other bottle is a base, all you need to do is, so long this one is an acid, by turning the blue litmus paper to red, I'll keep this, try that of a red litmus paper on other reagents. If any of the reagents happen to turn the red litmus paper back to blue, which is an indication that that very reagent is a base. Now this is the conical flask used for titration, titrating an acid and a base. So these are other forms of salt stored in different containers. This is the filter paper used. When we get to qualitative analysis, I'll tell you how the litmus paper can be, how the filter paper can be used. For example, today in volumetric analysis, having known all this, we need to conduct an experiment by titrating oxalic acid and potassium tetraoxomanganate 7. How do I do that? Look at the past question paper of the current exam on the board. Let's take this as an example. This is WAEC 2016 from Ghana. Assuming this question like this is given to you under volumetric analysis, how do I solve this? All you need to do is, one, this is the burette. In volumetric analysis, you need to adhere strictly to instruction. For example, this is the burette. Sometimes Normally, we pour the acid into the burette while we use the conical flask to titrate or pipette the base. But as you can see here, usually A stands for the acid, B is usually the base. But in this case, the instruction says put B into the burette and titrate it against A, which is the other way around. The real standard is meant to be put A into the burette because the burette is used to measure acid. So all I need to do if I'm to solve this question that is on the board, I need to keep to the instruction and solve this as follows. The instruction says A is a solution of 0.05 mole per dm cube oxalic acid. This is the molecular formula of oxalic acid. 0.05 mole per dm cube of oxalic acid. 0.05 here represents the molarity, which was the old name, but the current name is concentration in mole per dm cube. Now, the B part says the B is a solution of KMnO4. The IUPAC name is potassium tetraoxomanganate 7 of unknown concentration. Put B into the burette and perform the following exercise. Pipette 25 cm cube of A into a conical flask and add 10 cm cube of dilute H2SO4. If I'm to go by this, the instruction says put B into the burette. This is my burette. This is the retort stand. So I need to keep the instruction now. This is my funnel. We use the funnel to pour the reagent into the burette. Before then, you need to check the burette very well to ensure that there is no leakage. Then this is B. The instruction says put B into the burette. So you need to pour this and then up to the mark. The burette is calibrated down to 0 to 50. So all you need to do is you fill the burette to the 0 mark. All right. At this point, this is 50 cm cube of KMnO4, which is potassium tetraoxomanganate 7 solution. Then the instruction says also perform the following exercise. Pipette 25 cm cube of A. The A here is oxalic acid. Usually we pipette the base, but the instruction says pipette A, which is the acid. This is the pipette calibrated to 25 cm cube. So I need to take 25 cm cube of the solution A, which is the oxalic acid. There is a mark at this point. So this point is 25 cm cube. So all I need to do is to ensure that the reagent goes down to that very mark. All right. It's on the 25 cm cube mark now. I'll transfer it to the conical flask, and I'll release it there. At the end of this, you hit the conical flask with the burette once, then everything goes out. Then prepare 25 cm cube of A into a conical flask and add 10 cm cube of dilute H2SO4. This is my dilute H2SO4. This is an acid. It's an acid, so I need to acidify. Why are we adding this? It is to acidify the oxalic acid. Though it is an acid, but the instruction says add dilute H2SO4, 10 cm cube. This is a calibrated cylinder of 100 calibrated up to 100 mil. All I need to do is to take 10 cm cube of the acid. All right. This is 10 cm cube of H2SO4 acidified deoxalic acid. And the instruction says, and heat the mixture and titrate while still hot with B. That is, I need to heat the mixture for at least 40 to 60 degrees Celsius. So all I need to do now is to heat. All right, so from this point, you heat to a temperature of about 40 to 60 degrees Celsius. And you titrate as the reagent or the solution is still hot. You shake. So we are moving towards a point at which there will be a permanent color change. And that point is said to be the point of neutralization, the point at which an appropriate amount of the acid reacts with the base. The base here is the KMnO4. So this has to be done for 3. You need to carry out 3 consecutive titrations to ensure 3 concordant values. What do I mean by concordant values? The values need to be within a particular range. At that point, the value is said to be the titer value of this reaction, the point at which the acid and the base are at equilibrium. All right, from this point, there's a color change now. Initially, while titrating, it was colorless, but we can see that the color is, there's a fixed color now, which is an indication that the reaction has attained the point of neutralization. So what do I need to do? I need to read my value from the burette. At what point? So going by this, the point here is, the burette reading here is 18.50. 18.50. So all I need to do is to conduct this experiment for 3 consecutive times to obtain consistent or concordant values. When you do that, you need to tabulate your reading and solve accordingly. So how do I go about this? The table is as follows. Number 1, titration. This is titration. You have your final burette reading. In cm cube. Then you have the first one, or your rough. You have the first one, the second, and then the third titration. It depends on the number of titration you want to do. You can as well conduct just the rough and 2 titrations, or the rough and 3 titrations. The rough is just to make the students stable, a kind of remove tension from the students. Now, the first titration, as an expert, my value is 18.50. My second titration is 18.30, and the third one is 18.10. Okay? Okay, this is the final burette reading. My initial burette reading in cm cube I started from the 0 mark from the burette, which was 0.00, 0.00, all through, even from my rough. This is 18.70, my rough. So the volume of KMnO4 used that is, the KMnO4 is in the burette. So the volume of KMnO4 used is the difference between the final burette reading and the initial burette reading, which is 18.70, 18.50, 18.30, and 18.10. When it comes to titration, all the values must be in 2 decimal places. That's the standard. Then, what else do I need to do? To calculate the average titer value. I've gotten the volume of KMnO4 used. So the average titer value now becomes I need to take 2 concordant values here or 3 concordant values. But from what I've seen so far, I need to go for 2 values whose difference is either plus or minus 2. Plus or minus 0.2 difference. That's the standard. So the 2 values here are 18.5, which is the first titration, and 18.30, which is the second titration. So I'll go for 18.50 plus 18.30 divided by 2, which is the average titer value of the KMnO4 used for the reaction. The first question says, add this, okay? Repeat the procedure to obtain a consistent titer. That's the titer value that we've obtained so far. So what's next? The question says, from your result, calculate the concentration of B, the concentration of MnO4 in B in mole per dm cube. All I need to do is to write out the parameters. Write out the parameters. As you can see from here, I was given A is the solution of this. The 0.05 mole per dm cube here is the concentration of A in mole per dm cube. So concentration of A in mole per dm cube is 0.05 mole per dm cube. So we call this our CA, which is our CA. So our CA equal to 0.05 mole per dm cube. So we've gotten our CA to be 0.05 mole per dm cube. Put this exercise into this, okay, pipette 25 cm cube of A. So the volume of solution A, which is our VA, equal to 25 cm cube, 0.00 cm cube. Now the volume of B, volume of solution B, that is the VB, is equal to the average titer value obtained, because KMnO4 was our B. So this one is 18.40 cm cube. So we are looking for the concentration of B. So concentration of B, that is as in mole per dm cube, that is CB equal to question mark. So for the fact that we've gotten our CA, we've gotten our VA, we've gotten our VB, we are looking for our CB. There is a formula called Cavanagh. That is CAVA equal to CBVB. So using Cavanagh, equal to NA over NB, where Na equal to the mole ratio of the acid. This is the acid, oxalic acid, and the mole ratio here is 5. Equal to 5. Our Nb equal to 2. So we'll fix everything into this. We've known all this. So from this, our Ca becomes 0.05 multiplied by Va. Va from the question is 25 over the Cb, which is what we are to determine, multiplied by Vb, which is 18.4, equal to Na is 5 over 2, making Cb the subject of the formula. Making Cb the subject of the formula, Cb multiplied by 18.40 multiplied by 5 equal to 0.05 multiplied by 25 multiplied by 2. So our Cb, which is the concentration of B, becomes 0.05 multiplied by 25 multiplied by 2 over 18.40 multiplied by 5. So when you do that, at the end of the day, it becomes 0.05 multiplied by 25 multiplied by 2 equal to 2.5 over times 5 equal to this 9.92. So our Cb at this point becomes 2.5 divided by 92. 2.5 divided by 92, which is 0.0271 mole per dm cube. Now the standard is concentration in mole per dm cube must be in 3 significant figures. So the final answer becomes Cb becomes 0.0272 mole per dm cube, which is the concentration of B in mole per dm cube. The final question says, if in order to prepare B, 2.50 gram of impure solid was dissolved in 250 cm cube flask and made up to the mark, calculate the percentage purity of KMnO4. How do I do this? All I need to do is, a standard solution is being we are to prepare equal amount of an unknown solution of the sample in 1000 cm cube. That is, for question B, this is question A, the final answer to A. B says, okay, this is question C. This was A, the titer value was A. This is B, so this is C. C says if in order to prepare 2 points, to prepare B, 2.50 gram of impure solid was dissolved in 250. How do I go about this? If 2.50 gram of the solid dissolved in 250 cm cube, it implies that X gram of the solid will X gram of the solid will dissolve in 1000 cm cube, making X the subject of the formula. X becomes 2.50 multiplied by 1000 over 250. So X now becomes 2.50 multiplied by 1000 equal to this, divided by 250, which is 10 gram per dm cube. This is the mass concentration. The unit gram per dm cube is the mass concentration of the impure salt, the impure solid of the impure solid. All right. So for we to get the percentage purity, we need to know the concentration of the pure solid. How do I do that? I've known the concentration of the impure. How do I know the concentration of the pure, the mass concentration of the pure solid? Concentration in mole per dm cube equal to mass concentration in grams per dm cube over molar mass. And I need to get the molar mass of the KMnO4. The masses of the individual elements in the KMnO4 is given to us. So I need to get the molar mass of KMnO4. Molar mass of KMnO4 equal to K is 39.1 plus Mn is 54.9 plus oxygen is 16 multiplied by 4. which is equal to 54.9 plus 39.1 equal to 158. 158 gram per mole. The unit of molar mass is gram per mole. So I've known the molar mass of KMnO4. I've known the concentration in mole per dm cube of solution B. All I need to do now is to get the mass concentration of solution B. To do that, I need to fix in the values into this formula. It becomes concentration of B is 0.05. Concentration of B is 0.0271. 0.02717, which was the raw value. So I'm using the raw value instead of the approximate value. So from this place, it becomes 0.02717 equal to the mass concentration of B, mass concentration of B over the molar mass of B of solution B, which is over 158. So when you cross multiply, the mass concentration of B becomes 0.02717 multiplied by 158, which is 158 multiplied by 0.02717, 0.02717, okay, equal to 4.293 gram per dm cube. So this is the mass concentration of the pure KMnO4, of pure KMnO4. And I'm to determine the percentage purity of KMnO4. So percentage purity equal to mass concentration of pure over mass concentration of impure times 100 over 1 is equal to the mass concentration of the pure is 4.293 over the impure was 10 gram. This is the impure, the mass concentration of the impure, which is 10 gram multiplied by 100 over 1 times 100. divided by 10. So percentage purity of KMnO4 equal to 42.92%. This is the percentage purity of the KMnO4, which is 42.92%. And as you can see, it's a very simple calculation. All you need to do is keep to the steps, study harder, and it will help you when you come across questions like this. Thank you once again for staying with us. And don't forget that these apparatus are very important when it comes to volumetric analysis. Now, who can tell me the use of the Bunsen burner? All right, you're right. The Bunsen burner is used for heating. As you can see, we heated the reagent for 40 degrees.